So, in the last lecture we were discussing interface controlled growth of a stable nucleus, and now we want to examine diffusion controlled growth, where we had mentioned something about diffusion controlled growth, where diffusion processes will be involved in controlling the growth rather than the interface processes. For this, let us consider a hypothetical binary alloy. So, the phase diagram for this alloy could be something like this. This is a alloy between two components A and B, and let us say that we choose an alloy of composition C0 at a temperature, let us say T1. We are in the single phase region of this alloy, and let the single phase region be alpha. Now imagine that we suddenly bring the temperature down to some temperature T. So, we are at this point and we are now in the two phase alpha plus beta region. So, what we have now is a supersaturated solid solution of B in A, and hence this supersaturated solid solution will tend to break and beta nuclei will form at this temperature T, and once a stable nucleus form, that phase will tend to grow then. So, beta precipitates will grow, and they should grow. If you look at the equilibrium that is required, the alpha should have a composition of C alpha, and the beta should have, the beta precipitate that forms should have a composition of C beta according to this phase diagram. So, this C alpha composition of alpha is in equilibrium with the beta of composition C beta. So, we are talking about equilibrium kinetics here. So, let us try to model this as a one dimensional growth. So, let us try to model this as one dimensional growth. So, at time T is equal to 0, when we bring the alloy to temperature T, we quench it from T1 to T. So, at time T is equal to 0, all one has is composition C naught, and we have only the alpha phase. But as a nucleus forms and then it starts to grow, we have a picture like this. So, I have C naught here, I have let us say a slab of beta that is formed. So, I have a slab, imagine situation like this is my beta, this is my alpha, this is my alpha beta interface, and this is of thickness x, and this is at some time t. This composition of the beta that forms, so this is beta, out here is alpha, this composition is C beta, the equilibrium composition from the phase diagram. And let me mark the equilibrium composition for alpha here. So, let us assume local equilibrium at the interface. If we assume local interface at the interface, what does this mean? That in this region, the beta would have the equilibrium composition of C beta, and out here alpha at the interface would have a composition, equilibrium composition of C alpha, and far away from this beta precipitate, the composition will inside alpha would be C naught. So, hence the composition or the concentration profile within the alpha would be something like this. So, it will as one moves into the alpha away from the beta precipitate, the concentration inside the alpha would increase and reach the starting alloy composition of C naught. This is at some time t. Now, after an elapse of time dt, so this is at time t, at time dt this beta precipitate will grow by an amount dx, and the composition profile in the alpha would also change like this. So, the interface at time t was here, interface at time t plus dt has moved by a distance dx. So, this is the situation that we have. Now, in order to solve this in a kind of a simplistic manner, just to show what is the growth kinetics in this, we make a small simplification, and the simplification is that instead of assuming a curved profile like this, which actually is given by a complex function called the error function, we assume this profile to be a straight line. So, let me redraw this picture. So, simplify. So, in the simplified picture, the situation can be represented like this. This is C naught, this is C alpha, and within the alpha phase I have a linear concentration profile. And when after time dt the interface moves by a distance dx, so from at time t the interface is here, at time t plus dt the interface is moved by a distance dx, the profile becomes something like this, and that way the interface will keep moving. Now, what is our objective here? our objective here is to find out the velocity with which this interface will move and how the distance or the distance of the interface changes as a function of time. So, the velocity of the interface v is simply dx by dt. So, our objective here is to find this, and that would give us the growth kinetics. So, we will look at this simplified picture and attempt to solve this problem. Now, what are the processes that are happening? Remember, this is diffusion controlled process that we are looking at, and not interface controlled. So, the jumping of atoms across the interface is a very fast process, and therefore, we can neglect it, and the rate is essentially controlled by the rate of diffusion of atoms. In this case, one would need B atoms to diffuse, so there will have to be a flux of B atoms diffusing across the interface in order for this interface to grow, or for this interface to move, or for the precipitate to grow. So, let us look at it. What is the flux of B atoms? At what rate can B atoms move towards the interface? That flux, so that I am talking about, so flux of B atoms per unit area per unit time. If I call that as J, then this is given by d dc by dx. Now, what is this relation? This in fact is called the Fick's first law, which we will be discussing in subsequent lectures. For now, let us take this relationship as it is. D is called, in this case, the diffusion coefficient of B in A. dC by dx is the concentration gradient, which in our simplified approach, if you look at this diagram, the concentration gradient is a constant because we have assumed a linear profile of concentration. So, this is the rate at which B atoms are going to move per unit area per unit time. The velocity of the interface is dx by dt. So, at what rate essentially solute is getting added, B atoms are getting added to beta. So, we say that beta grows by dx in time dt. So, then rate at which solute, that is B atoms, is added is equal to, well, look at the amount of B atoms that are added, which is nothing but C beta minus C alpha. because here the concentration was C alpha, this concentration you can think is in terms of moles per unit volume. So, C beta minus C alpha multiplied by dx by dt. So, the concentration let us say is in moles per unit volume multiplied by the velocity of the interface dx by dt, and the units for this would simply be would become in terms of flux of B atoms in moles per unit area per unit time. So, this is the rate at which B atoms are getting added, this is the rate at which B atoms are arriving at the interface, and obviously for this rate and for this velocity the two have to match, have to balance, and therefore I can simply write C beta minus C alpha dx by dt to be equal to d dc by dx. Now let us look at it. What is dc by dx? If I go to my simplified representation here, dc by dx is the slope of this line, and that is nothing but C naught minus C alpha divided by some length L. Okay. So, I write this as d times divided by L. Now, what do we do with this relationship we have? We wanted to find this, so this is a unknown quantity for us. C beta, C alpha we know from the phase diagram. I know D, the diffusion coefficient of B in A, I can get from, there is a huge database of values of this diffusion coefficient D, or it can be obtained from experiment. So, the other unknown quantity that is left is L. I do not know what is this distance L. How do I find this distance L? Well, that is actually quite easy. In this system, there are no atoms going out of the system, no atoms coming into the system. There has to be a mass balance, atoms are conserved. So, if the concentration is increasing here, it is decreasing elsewhere, and hence if I look at this simple diagram, this area should be equal to this area for mass balance. So, from simple mass balance idea, the two areas are equal. So, what is this area? This is simply a rectangle, and this area is C beta minus C naught multiplied by x, and this is equal to the area of this triangle that is there, which is half C naught minus C alpha multiplied by L. So, now I can write down an expression for L, and that is simply rearranging the terms 2 C beta minus C naught divided by C naught minus C alpha multiplied by x. So, this is the value of the unknown quantity L. So, if I substitute this in this, I will get d times C naught minus C alpha, C naught minus C alpha square upon 2 C beta minus C naught times 1 upon x. So, this is the rate at which solute atoms are getting added, and that is equal to this on the right hand side. Now, this should be, this in fact is a fairly easy quantity to solve. It is a very simple differential equation. So, let me rewrite this as dx by dt equals d times C naught minus C alpha square upon 2 times C beta minus C alpha times C beta minus C naught times 1 upon x. Solving this, integrating both sides, x dx equals d times C naught minus C alpha square upon 2 times C beta minus C alpha times C beta minus C naught 0 to t dt, and this gives me x to be equal to C naught minus C alpha upon square root of C beta minus C alpha times C beta minus C naught, just simple rearrangement of terms, and this gives me how x varies as a function of time. So, the interesting thing is, this tells me that x is directly proportional to square root of dt, where d is the diffusion coefficient and t is the time. And now, if I look at velocity, which is dx by dt, well, that would be the same constant term C naught minus C alpha upon square root of C beta minus C alpha times C beta minus C naught square root of d by t, and that is simply that x is directly proportional to, not x but the velocity v is directly proportional to square root of d by t. So, one thing is clear, that growth rate is not a constant at a given temperature. In fact, it is going to be a function of time. And if I plot, for example, x versus t, if I plot x versus t, I will get a curve like this. So, as growth is taking place, the rate at which growth is taking place is continuously reducing with time. So, in fact, points to note here are: one, that growth is proportional to root dt, and hence this is called parabolic growth. 2, if you look at this, C naught minus C alpha, this is supersaturation. When you suddenly quenched from T1 to T, the alpha concentration was still C naught. So, growth is proportional to supersaturation. So, higher the supersaturation, higher is the rate of growth. As you can see in the velocity also, it is C naught minus C alpha, which is the supersaturation. And third, which I have already mentioned, velocity is proportional to square root of d by t, which means velocity reduces as time increases. Now, why is velocity reducing, or the growth rate is reducing with time? This could be understood if I relook at this diagram, that as the beta precipitate is growing, so I have C naught, I have C alpha out here, I have C beta, this is my beta has grown by x, and the concentration profile is this. Now, as growth takes place, let us say it has grown by delta x, the profile would become something like this. The slope, this is a straight line, that the slope will reduce, that is dc by dx reduces with time. As dc by dx reduces with time, remember the flux which is given by diffusion coefficient times the gradient of concentration. So, as the gradient of concentration is reducing, the flux of B atoms are reducing. So, if I look at this, this is reducing, and hence dx by dt has to reduce. So, this is the reason why growth is reducing with time. So, this is what in this lecture what we have discussed is diffusion controlled growth. So, in this lecture and the previous lecture, we have discussed two mechanisms of growth, the interface controlled growth and diffusion controlled growth. Interface controlled growth tells us that the growth rate will be constant for a given undercooling, while in the diffusion controlled growth rate is not a constant for a given undercooling. In fact, it keeps reducing as a function of time. With this, we finish our discussion on kinetics of growth, and what we have done in the last several lectures is we have understood nucleation rate and what factors control it. We have understood to some extent in the last two lectures growth rate. The two together will have to be considered to get overall transformation kinetics of phase transformation. So, with this I stop here in this lecture. Thank you.